Good day everyone. We are welcome back to our tutorials on introductory physical chemistry. If you could remember, in our last class we started discussing on thermodynamics. So today we are going to continue from reversible isothermal work done and internal energy. But before we begin, let's discuss on what reversible and irreversible process means. In our last class, we derived a formula for work done, which is W equals to minus P delta V. This work done is known as the what? Irreversible. Irreversible work done. So today we are going to see the reversible work done. Then, what is reversible? A process is said to be reversible when it takes place infinitesimally slowly, and a change in any property of the system an infinitesimal change in any property of the system can reverse the entire process. Meaning, no matter how slightly, when we say something is infinitesimal, that means something that is very small to the extent that you cannot measure. So, a reversible process is a process that takes place infinitesimally slowly. That means it takes place in the phase that you can't measure, and a change in any an infinitesimal change in a property of the system can change the entire state of the system. That is a reversible process. So today we are going to see the reversible isothermal work done. So from this formula, W equals to minus P delta V. Don't forget that this pressure we said is the what? External pressure. Because in thermodynamics, we always evaluate works in terms of the external pressure, not the internal pressure. So from here, but under reversible conditions, the P external used to be equals to P internal. And let's not forget that the external pressure is the same thing as what? Atmospheric pressure. That is the pressure acting upon the system. While the internal pressure is the pressure of the molecules in that system. So we all know that internal pressure, that is the pressure of the molecules in a system, is equals to what? Is equals to nRT over V. This is our internal pressure. So substituting this formula with delta V is for a measurable change. For an infinitesimal change, the W will be equals to minus P external dV. The difference between this and this is for a measurable change. For a measurable change. While this is for an infinitesimal change. And let's not forget, a reversible process is always takes place infinitesimally. So we are dealing with this second equation. So from here, if we substitute this formula into this, since P external equals to P internal, we can substitute this P external with this P internal, which is equivalent to this. Therefore, our dW will be equals to minus nRT over V dV. From here we can integrate this gentle equation. So on integrating both sides, we are going to have the integral of the W would give us W. W is equals to, keeping our number of moles constant, our molar gas, which is also a constant, and temperature. So they are going to get out of the integral sign. So we are going to have minus nRT. And so remind you, we are going to integrate this from V1 to V2. That is the limit of the integral. So if we integrate from V1 to V2, 1 over V dV. The integral of 1 over V is equals to ln V. So W will be equals to minus nRT ln V, and let's not forget it has a limit from V1 to V2, which is equals to minus nRT ln V2 minus ln V1. And of course, let's not forget from our law of logarithms, we know that ln V2 minus ln V1, or let's say for example log A minus log B. Since this ln is also log, is a natural logarithm of a number, so log A minus log B is going to give us the same thing as log A over B. So if we apply this principle, there we are going to have W is equals to minus nRT ln V2 over V1. This is our what? Reversible isothermal work done. And of course, we can express this in terms of pressure. Since from our Boy's law, we know that P1 V1 is equals to P2 V2. V2 over V1 from this formula is equals to P1 over P2. So from here, in V2 over V1, we can substitute it with P1 over P2. So we can rewrite this formula as, let me clean this place. We can write the formula as W is equals to minus nRT ln P1 over P2. Yes. Let's solve a question to understand the concept better. One mole of an ideal gas at 25 degrees centigrade is allowed to expand reversibly at constant temperature From volume of 10 liters to 20 liters, calculate the work done by the gas in joules and in calories. First, before solving any question as usual, we need to write out all the parameters. First, we are given a temperature. T is equals to 25 degrees centigrade, which is equals to 25 plus 273, which is equals to what? 298 Kelvin. That is our temperature, and it's expand from a volume of 10 liters. That is V1 equals to 10 liters, and V2 is equals to 20 liters. Then we are asked to calculate the work done by the gas in joules and in calories. We are not provided with the value of R, but let's not forget that our R is equals to 8.314 joules per mole per Kelvin. So let's not forget our formula is W is equals to minus nRT ln V2 over V1, which is equals to W is equals to minus, and our number of moles is 1. N is equals to 1. 1 times 8.314 times our temperature, which is 298 ln. V2 is 20 ln 20 over 10, which is the same thing as ln 2. So 8.314 times 298 ln 2. Yeah, our work done is equals to 1117.32 joules. Then from here, we are asked to calculate our answer in joules and in calorie. We know that 1 calorie is equals to 4.184 joules. Then what? X calorie will be equals to 7.32. X is equals to, from here, this time this divided by this, x is equals to 17.32 over 4.184, which is equals to 410 points, or let me write it somewhere here. X is equals to 410.45 calorie. So we are done with our question. This is the answer in joules, while this is the answer in calories. Then from here, let's head to the internal energy. Yeah, the internal energy. When we say internal energy, we are talking about the energy possessed by the molecules in the system. That is the internal. It is the total potential and kinetic energy of the molecules contained in a system. It is the energy used by those molecules within that system to do work. It is mathematically defined as U. Du is equals to dq plus dw. This is the internal energy, where this is the quantity of heat transferred into the system, while dw is the work done on the system by the surrounding. Yes, and I would like to elaborate more on this work. There is two types of work in thermodynamics. There's work done on the system by the surrounding. There's work done by the surrounding on the system. Work done on the system by the surrounding, that means the surrounding is doing work in the system. It used to be positive. Work done on the system by the surrounding. In this case, our work is positive. dW is equals to positive. While on the other way around, work done by the system dW is equals to negative. In this case, the system is doing work in the surrounding, meaning this dW is, how am I going to put it? If the system, if work is done on the system by the surrounding, meaning there's an input of work done, dW is equals to positive. While if the system is doing work, it is using some part of its internal energy to do some work. Therefore, it used to be negative. It is losing energy. Let's explain this further with an example. Let's solve some examples. We understand it better. Where is this question? Suppose the spring was wound and the juice of but 15 joules. Escape. Let's try to solve this. Suppose a spring was wound. 100 joules of work was done on it, but 15 joules escaped to the surrounding as heat. What is the change in internal energy of the spring? Initially, 100 joules of work was done on on that spring, meaning there's an input of work done. Our dW will be positive. Therefore, it's going to be 100 plus 100 joules. Do not need to write this plus, but had it been is negative, there's a need. But had it been here, 100 joules of work was done by the spring, this our 100 will be negative. But since it was done on the spring, not by the spring, it will be positive. So, but out of this 100 joules of work that was done on the spring, 15 joules escaped as heat. The Q is equals to what? 15 joules escaped as heat. Therefore, it's going to be negative because it escapes. This negative is signifying that the system loses some of its internal energy, so it's going to be negative. Then what is the internal energy of the spring? And of course we know internal energy du is equals to dq plus dw. But in this case our dq is negative. Therefore du will be equals to minus 15, which is our quantity of heat, plus 100. Our du will be equals to that is 100 minus 50, which is 85 joules. That is the internal energy of our system. Let's take another question. If an electric motor produced 15 kilojoules of energy each second, as mechanical work, and lost 2 kilojoules as heat to the surroundings, then the change in internal energy of the motor each second is let's solve this question. If an electric motor produces 15 kilojoules of heat each second as mechanical work and lost 2 kilojoules as heat to the surroundings, then the change in internal energy of the motor each second is. First, let's write out our parameters. Our work, dW, is equals to, it produces 15 kilojoules as mechanical work. By the time produced, we mean it is given out. Therefore, our work done is negative because it is producing the heat. It is not an intake of work done, but it is a production, meaning it is given out. So therefore, our dW is minus 15 kilojoules. That means it is losing 15 kilojoules each second as mechanical work. and further loses 2 kilojoules as heat. Therefore, our dq, in this cube, it is even clearly stated that it is a lost. It lost 2 kilojoules as heat. Therefore, our dq, quantity of work of energy, is minus 2 kilojoules. So therefore, our internal energy du is equals to minus 15. Du is equals to dq plus dw. Du is equals to dq. Sorry, our dq is minus 2 kilojoules minus 15 kilojoules. Therefore, our internal energy is equals to minus 17 kilojoules. Therefore, it is losing minus 17 kilojoules of energy each second out of its internal energy. Yeah, quantity of heat at constant volume. Let's see what used to happen to the internal energy of a system when heat is transferred into the system at constant volume. Constant volume process, we say it is otherwise known as isochloric process. So under isochloric condition, what used to happen to the internal energy of a system when heat is transferred into the system? So from here we know that du is equals to dq plus dw, but we know that dw, our work done, is equals to minus p dv. So at constant volume, that means there's no change in volume. Here is 0, therefore our dw is equals to 0 at constant volume. Our work done is equals to 0. Therefore du is equals to dq plus 0. Therefore our du is equals to dq. Let me write subscript v. This is telling us that any heat transferred into a system at constant volume will be used in raising the internal energy of the system. Therefore, the internal energy of a system is the same thing as the quantity of heat transferred into a system at constant volume. We've established this. What of at constant pressure? The heat transferred into or out of a system at constant pressure is known as the enthalpy the heat transferred into or out of a system at constant pressure is known as the enthalpy of that system, and it is often denoted as delta H. Let's see something. We know that U is equals to Q plus W. Then at constant pressure, our, let's see, QP, that is quantity of heat at constant pressure, is equals to what? U minus or before then, U is equals to QP at constant pressure minus PdV, or minus PV rather, because W is equals to minus PV. So if you substitute it here, we are going to get something like this. Our QP is equals to U plus PV, and we know that our QP, quantity of heat at constant pressure, is known as enthalpy, delta H. Therefore, our H is equals to what? U plus PV. We've established this. So, from this, we can head on to calorimetry.